First of all, regarding the compactness problem, so there was this issue with this delta T over T that I got stuck on. I just want to make something like a little bit clearer. To remind you, we tried to calculate the optical depth in the emission here and show that if we don't assume relativistic velocity, this optical depth is incredibly high. So for this optical depth, we needed to calculate the density of the photons, and the density of the photons is a function of the energy within each pulse. So this energy is the pulse energy, it's the energy within a single pulse, okay? And we divide it by the volume of the blob that is emitting this pulse and by the energy. So if we want to translate that to this is just the total energy in the burst times the time of the pulse divided by the total time of the burst itself. Now this quantity is invariant, okay? Because delta T over T change similarly, so this is an invariant quantity, and the total energy is invariant, okay? So this quantity is basically an invariant quantity, and only R square and Fe will be the quantities that are subject to the relativistic correction, okay? So that's why this term appeared here. Another thing that I wanted to tell you about, which regards relativistic velocity, is the only direct evidence for relativistic velocity that we had in gamma ray burst, let's say until last year, where we encounter a different evidence, but I will not talk about that. And this property is known as a jet break. Who heard about the quantity of jet breaks? Okay, that's good. Only a few hands, so it's okay. I'm not telling you something that you already know. So what is a jet break? So suppose that we have a jet coming out from some source, okay? The jet is moving with relativistic velocity gamma, okay? And since it moves with relativistic velocity gamma, every dissipation site, every emission site on the shock, the jet is moving in a medium and it's pushing a shock ahead of it. Okay, this is the shock, and this shock is radiating, it's emitting energy. Okay, so every emission site on the shock, the emission is beamed, as we discussed yesterday, and it's beamed into a cone with an opening angle, right, of 1 over gamma. Maybe I will plot that a little, I will draw it a little bit larger. Okay, now this part is dead, so I need to move here. Okay, so this is the jet. This is the emission sites. Let's plot 3 of them. And each one of them, the emission is beamed into a cone of 1 over gamma. Okay, so this is theta, and this is 1 over gamma. Okay? The observer, of course, an observer that is located here will see the emission. An observer that is located over here on the side will not see the emission, because all the emission is beamed to this direction. Now, as long as gamma is much larger than 1 over theta, okay? So which part of the jet, if I am an observer that is located exactly on the axis, which part of this jet will I be able to see? Will I be able to see the entire jet? No. Which part of the jet will I be able to see? So I will only be able to see the region in the jet from which the viewing angle, right, is smaller than 1 over gamma from the radial direction at that location. If this is a part of an arc, right, so each particle here is radiating in a radial direction and in a cone within 1 over gamma from the radial direction, okay? if this 1 over gamma part is not pointing towards me, I will not be able to see it. This part of the shock, for example, is radiating only within this direction, so I will not be able to see it. Okay? So I will only be able to see this part of the jet, as long as gamma is much larger than 1 over theta. Okay? So as the jet continues to move, it slows down. So gamma is decreasing. So the light curve that I will see, if I will plot the luminosity, okay, as a function of time, this is a light curve. What I will see a light curve that's starting to decrease. Why is it decreasing? Because the shock is slowing down and the emission becoming less and less strong. Okay? But another thing is happening. As the shock is slowing down, what is happening to gamma? It's decreasing. So what is happening to this angle of that I see the shock? It opens up. So I'm seeing more and more of the jet. Okay? So as time progresses, on one hand, each site is radiating a lower amount of energy. However, I'm seeing more and more parts of the jet. So these two things kind of act on a different direction, and this gives me a slope which is somewhat flatter than if I would have seen the entire jet. Okay? So what happens when I reach to a position where gamma is equal exactly 1 over theta? This is the jet. This is theta jet. Okay? What happened at this particular time? I'm seeing the entire jet, right? Because at this time, this is theta. Okay, now this now is theta, which is equal to 1 over gamma. Okay? So now I'm seeing the entire jet. Okay? At this point. Now the jet continued to slow down, right? Because it continued to collect more and more matter. So the shock slows down. But now what happens? Remember, I had two things that affected the light curve. First of all, the shock slowed down, so that's decreased the luminosity. Second, I saw more and more parts of the jet, so I saw more emission sites. But now when gamma is equal exactly 1 over theta, when the shock continued to slow down, I cannot see more parts of the jet because I already see the entire jet. So what will happen to the light curve now? It will break, because now I do not have the compensation from the part of the jet that I did not see before. So I will see a break. Okay? Now this break is very special, because this is a geometrical thing. So it will happen at the same time in all wavelengths. So it doesn't matter in which wavelengths I'm watching this jet, I will see this break. This is known as achromatic break, okay? Okay? And this is an indication that something geometrically happened here. And jet break, and usually what we see these jet breaks within about half a day after the gamma rays erupted. So I did not explain to you when I talked about gamma rays. When we discuss gamma rays, there are two parts within the burst. The first part, which is the gamma ray burst itself, is very short. It's about 100 seconds. And it's emit mostly in gamma rays and hard X-rays. Okay, the second part comes after this prompt emission, and this is, we call it as afterglow. Okay? And this afterglow is the emission from this forward shock that is propagating toward us. And this afterglow emission lasts for much, much longer time. And it's gradually, the peak energy is gradually shifting from X-rays to UV, to optical, to IR, and finally to radio. And the reason why it is happening is because we have a fast shock that is gradually slowed down, and as it slows down, it's radiate less and less, and the peak energy is smaller and smaller. Remember that the emission, the synchrotron emission, is a function of the ray of the Lorentz factor of the individual electrons times the Lorentz factor of the shock. Okay? So ni, the peak energy in the spectrum, ni peak, is proportional to gamma electron square times the Doppler factor. Right? So as the Doppler factor is the velocity of the shock. So as the shock slows down, two things happen. First, this decrease because the acceleration is not as efficient. And secondly, the boost is smaller. So the peak energy gets shifted from X-rays to UV to optical, gradually shifting. And also the total luminosity is decreasing. Okay? So this is the afterglow. And we see these jet breaks in the afterglow, not in the prompt emission. The prompt emission is too short. During the prompt emission, the jet is very relativistic. Okay? And this jet break is the only direct evidence that we have that gamma ray bursts are indeed jetted. Okay? And that the jets are relativistic. Yes?
So if we're not watching the jet head on, but watching it from an angle,
yes.
then say the lower part of the jet would break before the upper part, right? Because if, so the angle is opening up more and more, but you'll reach like the end of the jet, on the downside, say, or before you do it on the upside. Do you get what I mean?
Yeah, well, what will happen is that you will stop seeing this part, but you will continue to see this part. So what you will see is that you will see a more subtle break. Okay, you will see like a small break in the first part, and then another small break in the second part, but in the end, so this thing will just be smudged over a somewhat longer time, but in the end, you will see this. Okay? Another question on jet break? Okay, the main problem that we have is this is a very significant, a very distinct feature of jets. The problem is that we only saw it in half of the burst. And it is a big question that is still not really resolved why we didn't see any jet breaks in half of the other burst, from which we do see afterglow, and we should have seen a jet break. One possibility is that the jet break happened because there is a time difference between the observation of the prompt emission are done on gamma ray satellites. The observation of the afterglow emission are done on different instruments because the afterglow is coming on different wavelengths. And there is sometimes some time difference between these two observations. So it is likely that it's one possibility is that the jet break just happened within the window where we did not observe. Another possibility is that these jets are so powerful and the density and the medium is so tenuous that it takes very long time for the jet to slow down to a point where we will be able to see that jet break. And by that time, we do not observe it anymore. As more and more events are coming into our reservoir of observations, we spend less time in following them. Okay, because first event, second event are extremely interesting. 10th event is interesting, 100th event is already boring. So people don't spend resources in observing them. So it is likely that another possibility is just the jet break is happening too late. Okay? An indication from that actually happened in the short GRB event 170817, which was accompanied by gravitational wave. We saw an indication that indeed there is a jet only about 100 days after the event. So only now we truly understand that there was a jet there and that the jet was just not pointing at us, but that's a different story. Okay, so that's all I wanted to say about jet breaks. This is not what I want to discuss today. What I want to talk today is about accelerations. Okay, so the topic of today is jet acceleration. I will start with and I'm going to start with hydrodynamic jets. Okay? So imagine that we have a situation where I have a flow, that is collimated within some funnel. Okay, I have a velocity that's going in this direction. Okay, the funnel has a cross section A. Okay, and I want to see how the flow behaves as it's propagating up this funnel. Okay, so in order to do that, I just have conservation equations that I will use. Okay, first conservation equation is the conservation of mass. Okay, so the conservation equation, conservation of mass is the mass flux. Okay, the mass flux is just rho u c. Okay, and with all this discussion, to remind you, u is the 4 velocity, and it is equal to gamma beta I c. Okay. When I will use ijk indexes, it's for 3 velocity. Sometimes I will use the Greek letters, it's for 4 velocities. Okay. So I have mass flux, and also I have the stress energy tensor, which is basically the flux of energy and the flux of momentum. Okay, which is T mu nu. And this one is equal to W U mu U nu plus P eta mu nu, where eta is just the matrix minus 1, 1, 1. Okay? Another thing is that these indices, I will not deal anything with the upper and lower indices. You'll probably hear about them more next week. I do not know how to get indices up and down. Completely ignorant about that. If you have a question about how to raise or lower index, you can ask Sasha. He's an expert. Okay. Okay. So this is mass flux. This is energy flux and momentum flux. And if we want to conserve them, we just need to write the conservation equations. Okay. So the first, conservation of mass. Okay. So mass conservation is dq mu to dx mu, which is equal to d rho gamma to dt plus grad of rho gamma beta c, and this is equal to 0. Okay? So what I did is I took the 4-dimensional gradient of this, and the 4-dimensional gradient of this is equal to 0. Okay? So we're dealing with two things here. First of all, we're dealing with steady state. Okay? Nothing is evolving in our problem temporarily in time. So in a steady state, this is 0. Okay? And secondly, I'm doing like only 2D flow here. Okay? So in 2D, if I take the integral of that, so the integral of the gradient of rho gamma beta c dv, okay? So divergence theorem tells me that I can convert that to the surface integral of rho gamma beta C time dA. Okay? Now, which dA I am taking here? Okay, the dA that I'm taking here is, if I'm looking at this flow, I need to take a dA. If I want to do this integral in an easy way, I need to take a surface which is either perpendicular to the velocity or parallel to the velocity. Okay? So I'm taking a surface that looks something like that. Okay? This is the volume that I'm taking. Okay? So the surface is just the two bases and the envelope here. Now, since I have a velocity that is going in a funnel, velocity here is parallel to the surface and the velocities here are perpendicular to the surface. So beta dA here is 0. And I'm only left with beta times A here and beta times A here. Okay, so this integral is equal to rho gamma beta C times A in square bracket, which means that I need to take the value here and subtract it from the value here. Okay? So this is basically, if this is 2 and this is 1, so this is rho 2 times gamma 2 times beta 2 times A2 minus rho 1 times gamma 1 times beta 1 times A1. Okay? Everything is uniform. It's only a function of z. All quantities are only a function of z. Okay? So this means that the quantity rho gamma beta C times A is conserved, is constant. Okay? So this is for mass. I can do the same exercise for energy conservation and a similar exercise for momentum conservation and come out with 3 equations. So steady state conservation equation will tell me that rho gamma beta Ca is conserved, and I call this quantity Jm, the m for mass, because I will use current later. Okay? This is mass. Energy conservation is W gamma square beta A C is equal to the luminosity, which is also a conserved quantity. And first and last the momentum, W gamma square beta square plus P is equal to the momentum, which is Q. Anyone who did not do that, make an exercise, write this specifically for energy flux and momentum flux, okay, and apply this technique to get the conservation equation. It's a nice way to see that you understand how to do it. Okay? Okay, so now let's call this 1, 2, and 3. So now what we do, let's divide equation 2 with equation 1. So we're doing 2 divided by 1. And what we get is that we get that the quantity L divided by Jm is equal to W gamma divided by rho, and this is a constant quantity. Now this equation is just the relativistic form of the Bernoulli equation. Okay? This is just the relativistic form of the Bernoulli equation. And another 2 things that we need to do in order to get our relations is that I did not show you what W is. Okay? So W, which is the enthalpy per unit volume, is equal to rho C square plus the internal energy density plus the pressure. Okay? There is a connection between these 2 quantities, and this is come from the adiabatic, from and this, if we assume that there is an adiabatic evolution, okay, this is just the equation of state that will come in, and the equation of state will tell us that P is just equal to E divided by 3 because we are in a relativistic regime, okay? So this is equal to rho C square plus, and this is gamma adiabatic divided by gamma adiabatic minus 1 times P. This comes from the adiabatic equation, from the equation of state, sorry. And when we're dealing with gas with relativistic equation of state, what is the value of this? Anybody knows? 4 thirds, exactly. So this will become 4. So this is equal to rho C square plus 4 times P, okay? And we are working within the regime where the pressure is much larger than the rest mass energy density. So we're working within this regime that this is roughly equal to 4P. Okay, this is the regime where we work. Okay, and another thing, of course, rho is proportional to, yes, P is proportional to rho to the power of 4 thirds. Okay, so this is another form of the equation of state. So this means that rho is proportional to P to the power of 3/4. Okay, and this is proportional to W to the power of 3/4. Okay, so let's take the Bernoulli equation and write it using these assumptions. Okay, so what we have is that W gamma divided by rho, okay, is proportional to, we can say actually is equal to 4P times gamma divided by P to the power of 3/4. Okay? So this implies that this is proportional to P to the power of 1/4 times gamma, and this is equal to constant. Okay? So all I did is that I applied this assumption into the Bernoulli equation, and this is the relation that I got. Okay? So this means that P is proportional to gamma to the power of minus 4. Okay? Or I can write that P is equal to P0 gamma to the power of minus 4. Okay? And or that gamma is equal to P divided by P0 to the power of minus 1/4. So what does this mean? If I have my jet here, okay, and I have a pressure outside, okay, the jet maintains constantly, there is a pressure balance between the pressure in the jet and the pressure in the outside. Okay? So if the pressure, this is P external and this is P jet, okay? So if P jet is decreasing, then the Lorentz factor is increasing. So this is acceleration. Okay? So in order to get acceleration, I need a decrease in the pressure. Not very surprising. Okay? Now, what happened to the surface? Okay, what happens to A? Or what happens to the cross section of the jet as I accelerate? How does this behave? Okay, so in order to get that, all I need to do is I'm using this equation. AL, remind you, is equal to, here I'm using equation 2. And I'm trying to, I will try to get some constraint on how A behaves as a function of P. Okay, so I'm writing from equation 2. What I do is I take out A, which is equal to L divided by, okay, I will already write, this is 4P, which is W, times gamma square, times beta, times C. Okay? I can substitute, instead of gamma square, I can substitute that. and put that also in beta. So this is equal to L divided by 4p times p divided by p0 to the power of 1/4. Yes. And times, this is gamma. This is, it's minus 1/4. And here I have p0 divided by p to the power of 1/2 minus 1. This quantity is just gamma beta, okay, or u, okay? And this to the power of 1/2 times c, okay? All I did was substitute, instead of gamma and gamma beta, I substitute the result that we got here, okay? And so what I can do is I can take the derivative of a as a function of p and equate it to 0. I'm looking for extremum point of a. So how do I look for extremum point? I take a, derive it by p, take the derivative and equate it to 0. So dA to dP equal to 0 give me a extremum. And if I do that, I get that a get a minimum point, okay, when a minimum is equal to 3 square root of 3 times L divided by 8 P0 C, when P is equal to P star is equal to 4 divided by 9 P0. If you take this, derive it by P, equate it to 0, this is what you will get. You can do it yourself. Okay? First year derivatives. So let's try to understand what this means. Okay? So what does it mean that A is getting a minimum? It means that the jet shape actually look like something like this. This is the jet shape. Does it remind you of something? Exactly, Delaval nozzle. Okay, and if this is a Delaval nozzle, what is the speed here? Sound speed. Okay, this should be the sound speed. Let's see if this is what we get. Okay, so this is the pressure at the minimal point. Okay, so if this is the pressure at the minimal point, remember that gamma is equal to P divided by P0 to the power of 1 minus 1/4. So gamma in P star, right, is equal to P divided by P0 is just 4 divided by to the minus 1/4. This is P star divided by P0 to the power of minus 1/4. Okay, and this is equal to 9 divided by 4 to the power of 1/4, which is square root of 3 divided by 2. Okay, what is this quantity? Let's see, I don't know gamma, let's work in language of beta. Okay, so beta is equal to square root of 1 divided by 1 minus gamma square. Okay, and this is equal to square root of 1 minus 2/3, and this is equal to square root of 1/3. And what is square root of 1/3? Do you know? This is the relativistic sound velocity. When you have a relativistic gas, well, with equation of state that looks like W equal to 4p, the sound velocity is just square root of 1/3. So the gas here has a beta of square root of 1/3. So what is happening that as long as my velocity is subrelativistic, if I have a gas with relativistic temperature, okay, as long as the velocity is subsonic, if I want to accelerate, the funnel decreasing. When I get to a supersonic velocity, if I want to accelerate, the funnel is increasing. Okay? In other words, initially, all my pressure, what is pressure? Pressure is random motion. Okay, so what is acceleration? Acceleration is taking all this random motion and directing them in a single direction. This is acceleration. I'm not getting any more energy. All I'm doing is I'm shifting my energy from random motion to direct motion. So initially, okay, when I'm shifting this random moving energy into something that is more directed, I'm mostly increasing beta. Okay? So remember that in the mass conservation equation, I had rho, gamma, beta, A, and this is equal to a constant. Okay? So initially gamma is increasing, and also beta is increasing, and also rho is increasing. So A is decreasing. Okay? So this is what happens here. When I pass this sonic point, beta does not longer change mostly, because beta is becoming closer and closer to 1. So I cannot change that anymore. Okay? So what happens is that I'm taking most of this random motion and I'm putting it into rest mass energy. Now rho gamma is increasing. Okay? And so no, it's better to write it with this. Okay? So now P is decreasing, gamma is increasing, beta is not increasing that much, so A needs to increase as well. So over here, I'm mostly increasing beta. Over here, I'm mostly increasing the rest mass energy density. Okay? Okay. So this is all I had to say about acceleration of hydrodynamic jet. This, by the way, is known. This is a model that was done during the 70s. It was done by Blanford and Rees. This is known as the exhaust model. And this is the first time that it was shown that jets can accelerate by changing their opening angle, by changing the cross section. Okay? So now let's do a shift and stop talking about hydrodynamic jet, and let's see how magnetic jets accelerate. Okay? So now we move to magnetic jets. Okay. So before talking about acceleration, let's talk about jet launching. Okay? So in the hydrodynamic case, we assume that we already have a jet. We assume that it has some energy density, and it was already collimated. And so all that happens because of that. But people already asked me yesterday, how does jet get launched in the first place? Okay, so in hydrodynamic, I just put it by hand. But when I have magnetic field, I have a way to launch them from, let's say, something like first principles. Okay? So first of all, I want to tell you how magnetic jets are launched, and then I will tell you how they accelerate. So in order to launch a jet, what we need is we need a compact object or some sphere, okay? And I need magnetic field because I have magnetic jet. So what I assume here is that I assume, one, that I have a conducting sphere that rotate in the z direction. Okay, so I have rotation here. Okay? And I have magnetic field that are attached to this sphere. Okay? And it is magnetized. Okay, so what happens when I'm rotating here? it, I have velocity. Okay? So if I have something that is rotated and it is moving in magnetic field, I have force. Okay, so I have a Lorentz force, which is equal to QE plus QV cross B. Okay, this is just the Lorentz force. Okay, so V cross B. Okay, this is the magnetic field. It's sticking outwards. I have something that rotates. Okay, so right. So V cross B gives me a force that's going upward. So I have motions of charges, of positive charges to the north pole, motion of negative charge to the negative pole. Okay, so I have an opposite electric field pointing to that direction. Okay, so I have E which is equal to minus V cross B divided by C. Okay, and this is equal to omega R BP divided by C, okay, in the theta direction. Okay? Right. Okay. So, something is not right with the signs here. It should be the minus theta direction. Ah, right, because it is minus. No, something is not right here. Okay, this should be in the minus theta direction. I will correct it later. Just mark this. Okay? It's very hard to think on the board. Okay, so now let's assume that this sphere is infinitely conducting. Okay? So if this sphere is infinitely conducting, when it starts to rotate, what is it doing to the magnetic field? In an infinitely conducting sphere, when I move it, what is the magnetic field are doing? They are frozen to the surface, right? So if I'm moving an infinitely conductor, it is dragging the magnetic field with it. So if I will look at this sphere from above, and it is rotating in this direction, okay, and the magnetic fields are doing this, when I start to rotate them, they will get dragged in this direction. Okay? And this drag, what it will do, it will develop a toroidal component to the magnetic field. So just from rotation, I'm getting a toroidal component. Okay? And the value of this toroidal component, B phi, will be actually equal to omega R BP. So it will roughly be equal to V phi. This will roughly be equal to V phi divided by C times BP. Okay? More or less. So this is just omega R divided by C times BP, where R is the cylindrical radius. Okay? So I have an electric field, and this will be in the phi direction. So I have electric field. I have toroidal field. Both of them are perpendicular to each other. So what do I have if I have E cross B? What does E cross B gives me? A non-zero quantity of E cross B. What is that? This is a Poynting flux. Okay? So I get a Poynting flux, S, which is equal to E cross B divided by 4 pi C. Okay? And this is equal, I just multiply these two because E and B are perpendicular to each other. Okay? B phi is in the phi direction. E is in the minus theta direction, which I need to correct that. I did not correct that, but I will. Okay? So V, so Yeah, okay, so it's not in the minus, it's in the plus. I did it right. Okay. Wait. This is the directions are very, very confusing here. So if I'm rotating in this direction, magnetic field is sticking out here. Okay? So this is the plus phi direction. Again, I'm looking from above. Okay? If I'm rotating in this direction, what is the direction of B phi? B phi is directed here, and B P is directed here. Okay? So this is actually in the minus phi direction as well. So I have here, I have B phi going out, and I have E going this way. So this is B phi, this is E, and this is BP. Okay? So E cross B phi, where does it go? Radially outwards. Okay? So I have E cross B is directing outwards, and the value of that is just omega square R square divided by C times BP square. Okay? So this is a Poynting flux. And the Poynting flux is directing outwards. And this outward direction takes energy, takes electromagnetic energy, and this electromagnetic energy is flowing on radial direction, roughly on the direction of the poloidal field. Okay? And this is the energy of the jet. So all I need is a sphere with magnetic field that spreads that, and the sphere needs to be infinitely conductor or very highly conductor. I need to rotate it at fast velocity. Yes?
What happens in the case of a black hole?
So in a black hole, you don't really have a sphere, but you have a frame dragging. Okay? So in a black hole, you need to have two things. First of all, you need to have a plasma around you, because magnetic field cannot live by themselves on the horizon. If you just take magnetic field, they will disappear after dynamical time. Okay? So I need to continuously feed the black hole with magnetic field. I need plasma around it, because that the plasma will supply me currents, that the currents kind of hold the magnetic field by themselves. Okay? And I need the black hole to rotate. Once the black hole rotates, freight dragon will make sure that the magnetic field will rotate with it and produce the toroidal component. Okay? So I need rotation, continuously feeding, and plasma. Okay. So I have energy that is extracted from a black hole. I have the Poynting flux energy. Okay? And now I want to see what the flow is doing once it leaves the black hole. So I have motions along the field lines, along the poloidal field lines. Okay? And this motion is obeying, is just moving with the drift velocity, which Matt showed you. Okay? So plasma moves out along radial directions with the drift velocity. And what is the drift velocity? V drift or beta drift is equal to E cross B divided by B square. Okay? And this is just equal to E divided by B. Okay? This is the absolute value of the drift velocity. E divided by B. That's it. Total B. Yes?
I'm a bit confused. Why is B pi equal to B pi over C times BP? And also,
Okay.
shouldn't BP is diploidal?
Yeah.
Shouldn't that be like in the...
So BP is not exactly in the radial direction now, because I'm twisting it. So what I have is that BP that is pointing somewhere toward here. Okay? But when I'm looking at it at the side, this is BP. Why is B phi equal to V phi divided by C? So suppose that you had a magnetic field that is completely radial and starts to pull it on that side. Okay? The magnetic field has tension, so it's objecting into that. So it tries to adjust itself. Okay? It's like you try to pull a string that has some tension. So you create an angle here. Okay? The value, you create an angle which is basically something that looks like that. Okay? So this is a straight angle triangle. The value here is roughly equal to the velocity. Okay? This is the toroidal velocity. This is v. And since you're basically creating a wave here that continues to propagate outward, this will roughly be equal to the Alfvén velocity, which is roughly c. Okay? So you basically create an angle that the angle is dictated by the ratio between v and c.
But why is BP in the radial force almost in the radial? Like, shouldn't it be the colloidal direction?
Vp?
BP.
Yes.
Isn't that, because it looks like it's radial.
Yeah, because here I'm looking from the side. What is happening is that BP is a little bit, what I'm doing is I'm taking this sphere, I'm start to rotating it like that. So I had magnetic field that started radial, and it's kind of developed a tilt into this direction. Okay, you take something and you start to spin it like that. Okay, so the magnetic field getting dragged in the toroidal direction. But if I'm looking it from the side, you don't see it going in. Okay, you only see the part of when you view it from the side, you still see it as if it's radial. You don't change this direction, you only pull it inward into the board. Okay? So this is the drift velocity. So everything comes out from the black hole obeying this. It's moving within the drift velocity. Okay? So let's write 1 over gamma drift, which is equal to 1 over gamma square drift, which is equal to 1 minus beta drift square. And this is equal to 1 minus E square divided by B square. Okay? And I just do just bring them together, B square, and this is equal to B square minus E square. I can break B into two components, the phi direction and the poloidal component, the phi component and the poloidal component. So this is B P square plus B phi square minus E square. This is just algebra, nothing more. Okay? Now, this is 1 over the Lorentz factor. Okay? So 1 over gamma square, which is equal to Bp square plus B phi square minus E square divided by B square. Okay? Now I want to write these quantities in the terms in the rest frame quantities. Okay, everything is moving outwards. Everything is flowing out. It starts to accelerate. I want to write the quantity within the rest frame quantity. Okay? So since the motion, so here I'm assuming two things. First of all, okay, so first of all I'm assuming that gamma, that the velocity B, that the beta drift is roughly radial. And I'm also assuming that the poloidal field, although it's not exactly radial, it is roughly radial. So this is roughly aligned with BP, and this is roughly, and beta is roughly perpendicular to B phi. Now this is true at large distances. This is less true at small distances, but I will still going to assume that. Okay? So in this case, BP, if BP is directed along the motion, within the rest frame it doesn't change. So this is equal to BP square divided by B square, okay, plus And another thing is that this quantity, b phi square minus e square, is roughly the toroidal field within the rest frame. Okay, this is roughly b phi square divided by b square. Okay, so this is roughly the magnetic field in the poloidal magnetic field in the rest frame, and this is roughly the toroidal field in the rest frame. Okay, so I have two regimes here. I call this regime, so I name these things 1 divided by gamma square is equal to 1 minus gamma 1 square plus 1 divided by gamma 2 square. Where 1 over gamma 1 square is this, and 1 over gamma 2 square is this. So I have two regimes. Okay? So in the first regime, let's assume that within the rest frame of the flow, okay, first regime, BP is larger or equal to B phi. Okay? In this case, this is the dominant term. Okay? So here, 1 over gamma square is roughly equal to BP divided by B. So again, let's do another algebra. Very complicated algebra. This is square. I forgot the square. Okay? So then gamma square is equal to B square divided by BP square. I just flipped it. And this is equal to BP square plus B phi square divided by BP square, right? Because this and this are equal, and this I can break into two components. Okay? So this is equal to 1 plus B phi square. And to remind you what was B phi square was omega square r square divided by c square times BP, but BP is cancelled with this BP. So the expression that I'm getting is this one. Okay?
I'm confused. I thought little b was in the frame, like the rest.
True, but B, since motions are along the magnetic field, so BP in the rest frame is equal to BP in the lap frame. Okay? If you move along magnetic field, it doesn't change. If you move perpendicular to magnetic field, then you have a decrease by a factor of gamma. Okay? But I use this equality that B phi square minus E square is roughly equal to B phi in the rest frame. Okay? So here BP is not transformed. Okay? Okay? So how does this behave? Okay? So let's look at the at this quantity. So to remind you, I have a sphere, and the sphere rotates at the velocity of omega, okay? And I have a magnetic field around here, and motions here into the board, okay? The velocity is omega r, okay? This is the velocity into the board, okay? This is r, cylindrical radius, okay? So when r is increasing, the velocity is also increasing linearly with r until what radius? Can I continue doing that? Until a radius in which omega r is equal to c. Okay? In this radius, which I called the light radius, okay, omega times RL is equal to c, or RL is equal to c divided by omega. Okay? So I can change this omega square divided by c square by the quantity 1 plus r square divided by rl square. Okay? So when I'm in radius, in a location where r is much smaller than r square, gamma is roughly 1. It doesn't change. When I'm in locations which are much further away from the light cylinder, this quantity is much larger than r, and gamma square is roughly equal to r square divided by rl square, or gamma proportional to r. Okay? So I'm accelerating linearly with the radius. Okay?
Let me comment. Of course, it's Lorentz factor corresponding to the drift. It doesn't mean that the velocity of the plasma. But the beautiful theorem was proved that far from the light cylinder, the motion along magnetic field line is insufficient. And in the limit, the Lorentz factor of plasma lives just near this value.
Yes.
At the moment, Omer discussed the Lorentz factor of the drift motion.
Yes. And actually, the drift motion is not exactly along the poloidal field. It's actually perpendicular to all field lines, but it is roughly along the magnetic field.
Along the axis, this value is equal to unit. But of course, it doesn't mean that the plasma move it corresponds to the.
Yes, but since yes, but in the limit of infinite conductivity, this is roughly what the plasma is doing. Okay, so in the yeah, it's okay.
But doesn't this model break down between different light cylinders? Because like we were assuming the field lines are rigidly rotating. And so past that, when they can't really rigidly rotate anymore. So this should be bounded.
So what's happening is that when you're, I'll get to that. Okay, let's at this moment. This is the acceleration when you assume this, that within the rest frame BP is roughly equal to B phi. Okay? Now, what you say is relevant to the lab frame. Okay, so in the lab frame, remember that we want BP, which is roughly equal to B phi. So to BP in the rest frame, and you want B phi, which is roughly equal to B phi times gamma, right? Because magnetic field is perpendicular to the motion. So if I want to transform to the lab frame, it's B phi times gamma that I want. Okay? So this means that B phi will become increasingly more and larger than BP in the lab frame. What will happen is that, I will get to that, B phi and BP will become equal over here, and beyond the light cylinder, B phi will win. So B phi in the lab frame will become stronger and stronger relative to BP. So this happens because you can no longer co-rotate. So you're like dragging backwards, the plasma is dragging backwards, is dragging the magnetic fields with it. You become more and more dominantly in the phi direction. But this doesn't break. This continues to happen as long as you can maintain this. Okay? So, but that was a side remark. It doesn't matter. Okay? So, remember that we had two limits. We worked in the limit now when this is winning. Now let's look at the second limit when we are dominated by B phi in the lab frame. Okay, so in the second limit, so in the second regime, B phi is winning. Okay? So in the second regime, this is the dominant quantity. Okay? So 1 over gamma square is roughly equal to 1 divided by gamma 2 square, which is equal to B phi square divided by B square. Okay? So in this limit, gamma square is equal to b squared divided by b phi square, and this is equal to b divided by, so this is gamma, by the square root of b p square minus e square. And here, there is some algebra that is involved that I'm not going to go through. I will just state it. And this is equal to c times the curvature radius divided by r to the power of 1/2. What is the curvature radius? So if I have my jet, okay, the jet has some curvature. Okay? So RC is curvature radius. Okay? And the curvature radius RC, you can open Wikipedia and see that this is just equal to the absolute value of 1 plus dr dz to the power of square to the power of 3/2 divided by dr d square r dz.
If I'm not wrong, until now we didn't assume anything about the shape of the
Field lines.
jet.
Right. We did not assume anything.
So how can you what's the meaning of the radius?
And I'm going to show you.
Okay.
Okay? So this is roughly equal. So this is equal to 1 plus r tag square to the power of 3/2 divided by r2 tag. Okay? So what does this mean? So again, we have two regimes. One, I get this expression, and the other one I have roughly linear acceleration when I'm away from the light cylinder. Okay? So now let's take jets with certain shapes. So how do I set the shape of the jet? Okay? The jet is in pressure equilibrium with the medium. So all I need to do is to subscribe some pressure dependency of the medium as a function of jet, and this of the z, and this will give me a shape to the jet. Okay? So if I have a jet, this is the shape of the jet, and let's assume that the shape of the field lines, okay, let's assume that on each field line, okay, okay, z is proportional to r to the power of some alpha. Okay? So if alpha is equal to 2, I have a parabola. If alpha is equal to 0, I have a cylinder. Okay? So this means that r is proportional to z to the power of 1 divided by alpha. Okay? R tag is equal to z to the power of 1 divided by alpha minus 1. R2 tag is equal to z to the power of 1 divided by alpha minus 2. Okay? And the curvature radius here will roughly be equal to R2 tag to the power of minus 1. And this will be proportional to z to the power of 2 alpha minus 1 divided by alpha. Okay, I just took a common, just put them together. And this is proportional to r to alpha minus 1. Okay? So this is the curvature radius. And in this case, what I get is that gamma j in the second regime, and still in the second regime, is proportional to RC divided by R to the power of 1/2. And this is proportional to R wait, this is 2 alpha. R to the power of alpha minus 1. Okay? All I did is I subscribed what the curvature radius means. I wrote it as a function of R, and I put it in this expression, and I got the dependency of gamma as a function of R, knowing alpha. Okay? So, what does it mean? So alpha is a general parameter, so you can have different values. Okay? So when alpha is larger than 2, okay? What is R larger than 2? Alpha is larger than 2. Alpha is larger than 2. These are jets that are open shallower than a parabola. Okay? The larger alpha gets, when R is larger than 2, these are jets that are going closer and closer to the axis. Okay? Z, when alpha is infinity, Z is constant. When alpha is 0, I have a cone. Okay? When alpha is smaller than 1, I have something that opens like this. Something that opens like this. Okay? So large alpha means jets that are very, very, very narrowly collimated. Okay? So in this case, remember that this is the expression that I want. Okay? And when alpha is larger than 2, remember that I have gamma 2, this is gamma 2, and gamma 1 is equal to 1 plus R divided by RL square. And this is roughly equal to R divided by RL. Okay? So gamma 1 is linear with R. Gamma 2, when R is larger than 2, is go like a power which is larger than 1. So which one of the two? This is gamma 2. Which one of the two will win? Gamma 2 or gamma 1? Which is larger? Gamma 2 larger. So if gamma 2 is larger, okay, this quantity, 1 over gamma 2, is much smaller than this. So in the regime where alpha is larger than 2, if I'm looking at the whole expression of gamma, gamma 2 will be larger than gamma 1. So 1 over gamma 2 will be smaller than 1 over gamma 1. Okay? So this part wins. So I'm in the first acceleration regime. So when jets are very, very narrowly collimated, I am always within this regime. So when alpha is larger than 2, okay, gamma 2 will be larger than gamma 1, and 1 over gamma 1 will be larger than 1 over gamma 2, and gamma j will be proportional to R divided by RL, because this is the first acceleration regime. Did you follow this logic? This is the expression that I need. This is the full expression of the acceleration. So when the jets are narrowly collimated, again, gamma 1, which is proportional to R, is developing slower than gamma 2, which is proportional to alpha minus 1, which is a quantity that is larger than 1, because something that 3 minus 1 is 2. Okay, so gamma 2 is developing faster than gamma 1, is becoming larger. So 1 over gamma 2 is smaller than 1 over gamma 1, because I'm just taking the reverse of it. Okay? So this quantity wins. So in narrowly collimated jets, I'm in the linear acceleration regime. Okay? What happened on the opposite side? You can guess. In the opposite case, when alpha is smaller than 2, Okay? So when alpha is smaller than 2, gamma 2, that is proportional to r at the power of alpha minus 1, is smaller than r. It's developing slower than r. So if it's developing slower than r, then gamma 2 will be smaller than gamma 1. And this means that 1 over gamma 2 is larger than 1 over gamma 1 square. And this means that this term wins. So we are in the second acceleration regime. Okay? And in the second acceleration regime, okay, gamma is proportional to r to the power of alpha minus 1. But since alpha is smaller than 2, this quantity develops slower than linearly. So the acceleration is less efficient. In other words, if we are in a regime where poloidal and toroidal fields are roughly equal to each other within the rest frame, I'm accelerating very efficiently. If I'm in a regime where I am dominated by toroidal field in the rest frame, my acceleration is not efficient. I'm accelerating less than this. This is the most efficient way to accelerate. So the acceleration in magnetic jet, unlike in hydrodynamic jet, depends both in the geometry of the jet and in the configuration of the magnetic field. In order to get very good acceleration in magnetic jets, I need jets that are very, very narrowly collimated. Okay? That's the conclusion from this drill. Okay? I will stop here. Any questions? That was a hard day. Yes.
In the beginning, you said about the new evidence for jets in gamma-ray birds, but you didn't say what was this evidence.
Okay, so this is a little bit tricky. What's happening is that, you remember when I told you that when the jets are very narrowly beamed, you need to be on the axis of the jet in order to see it. If you're off axis, you won't be able to see it. What you will see emission that is much weaker. Why is it much weaker? Because it is unbeamed. Okay? But as the jet continues to decelerate, what's happening is that the beaming becoming less efficient, and you see more and more of this unbeamed radiation. So when you will look at the light curve, you will see something that is gradually increasing. At some point, when the jet will go into your line of sight, you will start to see it, but then again, you will have something that is like a jet brake, because now you see the entire jet, and now as the jet continues to decelerate, you start to not see it. Okay, so what you see, instead of something that goes down and break, you see something that goes up and break. And you see it, the thing is that you see it mostly in the radio, for other reasons. And this is exactly what we saw in the observation of 170817. We saw a light curve that gradually rise in the radio within 100 days. And we waited for that break, because this break would tell us that what we see is a jet, that we see a jet break. And after about 180, between 100 and 180 days or something like that, now we're seeing the jet break. So this is an evidence not only that there is a jet, but it is an off-axis jet. Okay? Yes?
How can the Keplerian disk maintain its magnetic structure during the rotation?
Okay, so here I'm not discussing disks. I'm discussing infinitely conducting spheres. So here the magnetic fields are locked onto the sphere. I have no problem with that. Anything related to disk, magnetic structure is not very well it's not very clear that you do develop this large-scale magnetic field. In order to have this acceleration, I need that the magnetic field will extend outside of the light cylinder. Okay, remember that this very efficient acceleration is only true when my radius is larger than the light cylinder. Okay? So I want my magnetic loop to extend to very, very large radii in order for this to work. So I need large structure magnetic field for magnetic jet acceleration. In disks, it is actually hard to do that. You need a very efficient dynamo that will sustain over a long time in order to give you this very large loop. And there is, until now, I don't think that there are any evidence that this large-scale magnetic field actually exists in disks. So the how, I have no answer because I don't know if the if exists. Yes?
So you might have mentioned this, I might have missed it, but so when you say there is efficient acceleration, which you have there on the bottom and the middle blackboard, where do you get the collimation from that?
Okay, so in order to collimate the jet, I need a medium. I need a medium with some pressure profile. Now, the jet and the medium maintain balance between each other. So again, remember, we're working in the assumption of a steady state. The jet is not expanding. There is a force balance on the edge of the jet. Okay? So the force balance is that the pressure here is equal to the pressure here.
All right. So there is nothing about the collimation in this derivation?
No. I still did not discuss anything about the collimation, and I assume that the jet is collimated. Also, in the hydro case, I did the same assumption, that the jet is already collimated. Yes?
Maybe, I guess it's before you mentioned, but I lost it. Do you expect any physical discontinuity when you have the linear acceleration mechanism as the dominant one, and you go to radius bigger than the light radius?
No. It will continuously accelerating beyond what is happening. What will happen that at the light cylinder, okay, you started with gamma equal 1, and at the light cylinder, gamma is roughly square root of 1. So at the light cylinder, it's actually the radius where you become relativistic.
Yeah.
At radii smaller than the light cylinder, you are subrelativistic. Your Lorentz factor is 1. Above the light cylinder, this is the radius where you become relativistic. That's why you need, in order to get relativistic jet, that's what you need, magnetic field that extend beyond the light cylinder. Because only there your Lorentz factor is large enough. The main thing here is that you need strong enough collimation in order to get your acceleration. More questions? Yes?
Is there a limit to non-relativistic rays in this equation?
Again, sorry?
Is there a limit to non-relativistic rays?
There is a limit to the non-relativistic case. However, I did not work it out, so I don't know how to develop it. But there should be. There should be. So basically in the non-relativistic case, you are below the light cylinder. Your rotational velocity are very low. So RL, which is C over omega, is very, very large. So you are always inside the light cylinder. Okay? So inside the light cylinder, you always have co-rotation. So the main regime is this one. In the non-relativistic regime, you usually here. Okay? Yes?
So the expression again, R over RL, when does that break down? It has to break down at some point, right? Else you would get infinite acceleration.
That's true. It will break down. In order to have this acceleration, like in the hydrodynamic case, you need that most of your energy will be in magnetic field. So most of the energy in magnetic field is that B squared divided by 4 pi is much larger than rho C squared. The ratio between these two is known as the sigma parameter. So you need a sigma parameter which is much larger than 1. This is like the enthalpy, which is much larger than 1. Okay? So this will break down while sigma will reach values that are close to 1. So you transfer most of your magnetic energy into matter. Okay? Tomorrow I will show you other ways where it breaks down. Okay, you also need, in order for this to break down at sigma equivalent, you need very, very small opening angles. If you have large opening angles, something else reaches. you become uncausally connected. So two things need to happen. First of all, you need to be causally connected, and I will explain what is causal connection tomorrow. Okay, you need to be causally connected to the axis, and you need to be magnetically dominated.
Okay,
Last one.
last question.
In the hydrodynamic case, you used the reduced equation of state.
Yes.
Is it correct near the source of the jet? Because the flow may be non-relativistic.
Yes, remember that I mentioned at the end of the talk yesterday that in order to get relativistic jets, you need to accelerate very light material. You need to put a lot of energy into a very small amount of matter. When you do that, by definition, your equation of state is very relativistic. Okay, when you have a non-relativistic equation of state, you don't have enough energy to push your material to high Lorentz factor. So you need that. Yeah, you cannot do that when you have a non-relativistic equation of state.